Welcome to DAR Tutors. Today, we're going to dive into the world of discrete random variables, a key topic in IB mathematics, analysis and approaches higher level. By the end of this video, you will be able to construct probability distributions, calculate their mean and standard deviation, and understand the properties of linear transformations on these variables. We'll cover the fundamental concepts of mean and standard deviation, their relationship, and how they change when you apply a linear transformation to a random variable. Let's get started with our first problem. Our first problem asks us to consider a die numbered 1, 1, 2, 3, 3, 3. First, we need to construct the probability distribution for the random variable x. This means we need to list every possible outcome, x, and its corresponding probability, p, of x equals x. To do this, we'll count how many faces show each number. The total number of faces is 6. For the number 1, there are 2 faces. So the probability of rolling a 1 is 2 out of 6, or 1/3. For the number 2, there is only 1 face. So the probability is 1 out of 6. And for the number 3, there are 3 faces. The probability of rolling a 3 is 3 out of 6, or 1/2. We can now put this into a table. The possible outcomes x are 1, 2, and 3. The corresponding probabilities p ski x are 1/3, 1/6, and 1/2. Remember, the probabilities must sum to 1. Next, we'll find the mean of this distribution, often denoted by the Greek letter mu. The mean, or expected value, ex, tells us the average outcome we'd expect if we rolled the die many, many times. The formula for the mean of a discrete random variable is the sum of each outcome multiplied by its probability. That is, mu equals the sum of x times p of x equals x. Let's apply this to our problem. We multiply each outcome by its probability and then sum them up. So ex equals 1 times 1/3 plus 2 times 1/6 plus 3 times 1/2. This simplifies to 1/3 plus 1/3 plus 3, 2. Converting to a common denominator of 6, we get 2, 6 plus 2, 6 plus 9, 6, which equals 13, 6. So the mean of the distribution is 13, 6, or approximately 2.167. This means that on average, we expect to roll a number around 2.167. Our final task for this problem is to find the standard deviation, sigma. The standard deviation is a measure of the spread or dispersion of the data. A smaller sigma means the outcomes are tightly clustered around the mean. To find the standard deviation, we first need to calculate the variance. The variance, denoted as sigma squared, is the expected value of the squared difference from the mean. The formula is the sum of x minus mu squared times px. This formula can be a bit tedious to use. A more efficient and commonly used formula for variance is sigma squared equals the sum of each outcome squared times its probability minus the mean squared. This is often written as the expected value of x squared minus the expected value of x squared. Let's calculate ex squared first. Ex squared is the sum of each outcome squared times its probability. So it's 1 squared times 1/3 plus 2 squared times 1/6 plus 3 squared times 1/2. This simplifies to 1/3 plus 4, 6, or 2, 3 plus 9, 2. The sum is 31, 6. Now we can find the variance. Var x is 33, 6, our ex squared, minus 13, 6 squared, our mean squared. This is 33, 6 minus 169, 36. Getting a common denominator, we have 198, 36 minus 169, 36, which equals 29, 36. Finally, the standard deviation is the square root of the variance. So sigma is the square root of 29, 36, which is about 0.898. The standard deviation tells us that, typically, an outcome deviates from the mean by about 0.9. In this problem, we've successfully constructed a probability distribution and calculated its mean and standard deviation. We've seen how to build the foundation for analyzing discrete random variables. Our next problem introduces a random variable x with a probability mass function. A probability mass function, or PMF, is simply a formula that gives the probability for each possible value of x. Let's first construct the probability distribution table by plugging in the values for x. When x is 1, px of 1 is 1 squared plus 1 all over 20, which is 2 over 20 or 1 over 10. When x is 2, p equals 2 is 2 squared plus 2, which is 6 over 20 or 3 over 10. And when x is 3, p x out of 3 is 3 squared plus 3, which is 12 over 20 or 3 over 5. So here is our complete probability distribution. Let's quickly verify that the probabilities sum to 1, 1 over 10 plus 3 over 10 plus 6 over 10 equals 1. It checks out. Now let's calculate the statistics for this distribution, starting with the mode. The mode is simply the outcome that occurs most frequently, or the one with the highest probability. Looking at our table, px1 is 110, px2 is 310, and px3 is 610. The highest probability is 610. This corresponds to the outcome x is 3. Therefore, the mode of this distribution is 3. It's the most likely result. Next, let's find the median. The median is the value x for which the cumulative probability is at least 0.5 for the first time. In other words, it's the middle value. We can find this by looking at the cumulative probabilities. For x1, the cumulative probability is p as x1, h1 under 10, asasan, which is 0.1. This is not yet 0. For x2, the cumulative probability is p x2, x plus 1. P x 2 equals 1 under 10 plus 3 per 10 equals 410, which is 0.4, still not 0.5. For x of 3, the cumulative probability is PAO x of 3. And see, option spots 3 to 10, 6 to 10, c equals 10 out 10, which is 1. This is the first time the cumulative probability is 0.5 or greater. Therefore, the median of this distribution is 3. Now let's calculate the mean mu and the standard deviation sigma for this distribution. We'll use the same formulas as before. The mean EX is the sum of x times PXE dx. Plugging in our values, we get 1 times 110, plus 2 times 3 times 10, plus 3 times 610. This simplifies to 110 plus 610 plus 1810, which sums to 2510 or 2.5. So the mean is 2.5. Now for the standard deviation, we'll first find the variance using the formula EX squared minus EX squared. First, EX squared is 1 squared times 110, plus 2 squared times 3 per 10, plus 3 squared times 610. This becomes 110 plus 1210 plus 5410, which sums to 6710 or 7. Now we can find the variance. VI our x equals 6.7 minus the mean squared, which is 2.5 squared. This is 6.7 minus 6.25, which gives us 0.45. So the variance is 0.45. Finally, the standard deviation sigma is the square root of 0.45, which is approximately 0.671. Here we've successfully worked with a probability mass function to find the mode, median, mean, variance, and standard deviation. It's a comprehensive look at the descriptive statistics for a discrete random variable. Our next problem asks us to prove a very important relationship between variance and expected value. This is a foundational result you should know for your exams. We'll start with the definition of variance on the left-hand side and manipulate it algebraically to reach the expression on the right. Let's begin with the definition. Variance is the expected value of x minus mu squared. First, we'll expand the term inside the brackets. X minus mu squared is x squared minus 2 mux plus mu squared. Now we can use the linear properties of expectation. The expected value of a sum is the sum of the expected values. So this becomes the expected value of x squared minus the expected value of 2 mux plus the expected value of mu squared. Let's analyze the terms one by one. The first term, ex squared, is what we want. The third term, e mu squared, is the expected value of a constant. By definition, mu is a fixed value, the mean. The expected value of any constant is the constant itself, so e mu squared is just mu squared. The second term, e2 mux, involves a constant multiplier, 2 mu. Another property of expectation is that you can pull constants out. So this is 2 mu times the expected value of x. But we know that the expected value of x is just our mean, mu. So this term becomes 2 mu times mu, which is 2 mu squared. Now let's substitute these back into our expression for variance. We have ex squared minus 2 mu squared plus mu squared. Combining the mu-squared terms, we get our desired result. E x squared minus mu squared. We have proven the alternative formula for variance. Let's emphasize this. The variance of x is the expected value of x squared minus the square of the expected value of x. This is a powerful and efficient formula for calculating variance. We've seen the formula for variance in terms of Ex and Ex squared. Now let's explore how the expected value, variance, and standard deviation change when we perform a linear transformation on a random variable x. Suppose we have a random variable x with mean mu and variance sigma squared. What happens if we create a new random variable y, where y equals a times x plus b? Here a and b are just constants. Let's start with the mean, or expected value, ei x ex plus b. Using the linear properties of expectation we saw earlier, this becomes a times ex plus eb. We know ex is mu and eb is just b. So the expected value of our new variable y is a times mu plus b. This is a very intuitive result. If you scale the variable by a and shift it by b, the mean scales by a and shifts by b. Now for the variance. This is where things get a bit more interesting. Variance measures spread. Vari ici var ax plus b. Let's think about the transformation. What does the constant b do to the spread of the data? Adding a constant to every outcome simply shifts the entire distribution. It doesn't change how spread out the values are. So the b term has no effect on the variance. What about a? Multiplying by a constant a does change the spread. It scales the distances between outcomes. The key here is that variance is based on the squared deviations. So the scaling factor becomes squared. Var ax plus b is equal to a squared times var x. Finally, for the standard deviation, we just need to take the square root of the variance. Sigma of y is the square root of var y, which is the square root of a squared times var x. This simplifies to the absolute value of a times sigma of x. We use the absolute value because standard deviation must be positive, and a could be negative. Notice the b term again disappears, as it doesn't affect the spread. Let's summarize these crucial properties. If y equals ax plus b, the mean is a times mu plus b. The variance is a squared times sigma squared, and the standard deviation is the absolute value of a times sigma. You should memorize these three rules, as they are fundamental to working with linear transformations of random variables. Let's apply these properties to a concrete example. Suppose a random variable x has a mean of 8.1 and a standard deviation of 2.37. We want to find the mean and standard deviation of a new variable y, which is defined as 4x minus 7. Here our constant a is 4 and our constant b is 7. We can use the formulas we just derived. For the mean, we use the rule ax plus b equals aex plus b. So ey equals e4x, 7 equals 4 times ex minus 7. We substitute the given mean of 8.1 for ex. This gives us 4 times 8.1 minus 7. That's 32.4 minus 7, which is 25.4. So the mean of y is 25.4. Now let's find the standard deviation of y. For the standard deviation, we use the rule sigma ax plus b equal absolute value of a times sigma x. So sigma y equals sigma 4x, or 7, equals the absolute value of 4 times sigma x. The absolute value of 4 is just 4. We substitute the given standard deviation of 2.37 for sigma slash x. So sigma y is 4 times 2.37, which equals 9.48. The standard deviation of y is 9.48. Notice how quickly we could solve this problem by applying the properties of linear transformations. We didn't need to know the entire probability distribution for x, only its mean and standard deviation. To help you prepare for your IB exams, we've prepared 5 IB-style practice questions that cover the concepts we've discussed today. First question. A discrete random variable x has ptex equals x, equals k 2x plus 1, for x equals 1, 2, 3, where k is a constant, find k. Take a moment to solve it on your own before I reveal the solution. Okay, let's look at the solution. The fundamental principle here is that the sum of all probabilities in a distribution must equal 1. So we sum the probabilities for x1, x2, and x3. This gives us k times 2, 1 plus 1, plus k times 2 to 2 plus 1, plus k times 2 to 3 plus 1, which must equal 1. Simplifying inside the brackets, we get 3k plus 5k plus 7k equals 1. Adding these up gives 15k equals 1. Therefore, k is 115. Question 2. A random variable x has mean 4 and variance 9. Find e2, 3x, and var 4. Remember the properties of linear transformations we just learned. Pause the video and give it a try. And here is the solution. First, for the expected value, e2/3x. This is e's 3x plus 2. Using our property, it's 3 times ex plus 2. We substitute the given mean of 4. So we have 3 times 4 plus 2, which is 12 plus 2, giving to 10. The expected value is 10. Now for the variance, var 4x. Using our property, this is the square of 4, which is 16 times var x. We substitute the given variance of 9, so we have 16 times 9, which equals 144. The variance is 144. Question 3. A random variable x has mean 5 and standard deviation. 2. Find var 2x plus 3. Be careful with the standard deviation. See if you can convert it to the variance needed for the formula. Let's go through the solution. First, we are given the mean ex equal 5 and the standard deviation sigma x equals 2. Our formula for variance requires the variance var arc. Remember, the variance is the standard deviation squared. So var x equals 2 squared, which is 4. Now we can use the property for the variance of a linear transformation. Var 2x plus 3 is a squared times var x. Here, a is 2, so it's 2 squared, or 4, times var x. Plugging in our variance of 4, we get 4 times 4, which is 16. The variance of 2x plus 3 is 16. This shows the importance of using the correct statistic in the correct formula. Question 4. A biased pentagonal die has probability px equals x as shown in the table. What is the value of A? This is very similar to our first practice problem. The key is knowing the property that the sum of probabilities is 1. Let's check your answer. Again, we use the rule that the sum of probabilities is 1. We add all the given probabilities, 1 over 6, 1 over 3, 1 over 12, and the unknown A, and set the sum equal to 1. To make the addition easy, we find a common denominator, which is 12. We convert each fraction. 2 over 12, 4 over 12, 1 over 12, and 2 over 12. Adding the fractions, we get 9 over 12. So, 9 over 12 plus a equals 1. This means a must be 3 over 12, which simplifies to 1/4. So the probability of rolling a 4 is 1/4. Our final question is a great example of a multi-part IB question that tests several concepts at once. This problem combines finding the constant k, calculating a new expected value, and finding the variance of a linear transformation. Work through each part carefully. Okay, let's break it down. First, for part A, we find k by setting the sum of probabilities equal to 1. The sum of k squared for x from 1 to 4 is k times 1 squared plus 2 squared plus 3 squared plus 4 squared. The sum of the squares is 1 plus 4 plus 9 plus 16, which is 30. So 30k equals 1, and k is 130. For part B, we need to find the expected value of 2x. This is simply 2 times the expected value of x. First, we must find e's. Ex is the sum of x times pecx. Using our value for k, this is 130 times the sum of x times x squared, which is x cubed, for x from 1 to 4. That's 130 times 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. The sum of the cubes is 1 plus 8 plus 20 plus 64, which is 100. So ex is 130, or 10(3). Then e2x is 2 times 10(3), which is 23. Finally, for part C, we find var 3x plus 1. This is 3 squared, or 9 times var x. We need var x, which we can find using ex squared. Ex squared. Ex squared is k times the sum of x to the second times px equals x. That's k times the sum of x to the fourth for x from 1 to 4. Actually, ex squared is k times the sum of x to the power of 4. That's 130 times 1 plus 16 plus 81 plus 256, which is 130 times 354, or 59.5. Now we find var x. It's 59.5 minus 10.3 squared. This is 59.5 minus 109. Finding a common denominator of 45, we get 531.45 minus 5, which is 31.45. Finally, var 3x plus 1 is 9 times var x. So it's 9 times 31.40. The 9 and 45 simplified to 1 and 5, leaving us with a final answer of 31.5. Let's quickly recap what we've accomplished today. We learned how to construct probability distributions, both from direct descriptions and probability mass functions. We calculated key descriptive statistics: the mode, median, mean, and standard deviation. Most importantly, we explored how a linear transformation y equals ax plus b affects the mean, variance, and standard deviation of a random variable. We saw that the mean scales and shifts, the variance scales by a squared, and the standard deviation scales by the absolute value of a. We then applied all these concepts to several IB-style problems. Mastering these concepts is crucial for success in IB Mathematics AAHL. Remember to practice regularly. For more help with these topics and personalized support, please visit DAR Tutors. Thank you for watching.